Keep in mind this block diagram for the communication system that we are studying. Lemma 11.15 is the data processing theorem, which says that the mutual information between W and W hat is less than or equal to the mutual information between X and Y. Here is the sketch of the proof. Like in the discrete case, the Markov chain W, X, Y, W hat can be established. W and W hat are discrete random variables. The random sequence X is real, but it has a discrete distribution. The random sequence Y is real, and it has a continuous distribution. Therefore, Y needs to be handled with caution. In particular, the existence of the conditional PDF Fy given W hat needs to be established so that the mutual information of X and Y conditioning on W hat can be defined. For the technical details, please refer to the textbook. We now prove the converse of the channel coding theorem. Let R be an achievable rate, that is, for any epsilon greater than 0, there exists for sufficiently large n an nm code such that 1 over n times log m, that is the actual rate of the code, is greater than R minus epsilon, and lambda max, the maximal conditional probability of error, is less than epsilon. Now, consider log m is equal to entropy of W. This is so because the message is chosen uniformly from the message set. This can be written as the entropy of W given W hat plus the mutual information between W and W hat. Now the mutual information between W and W hat by the data processing theorem is less than or equal to the mutual information between X and Y. This can be further written as the differential entropy of Y minus the differential entropy of Y given X. Now, the differential entropy of Y by the independence bound is upper bounded by summation I, the differential entropy of Yi. The differential entropy of Y given X is equal to summation I, differential entropy of Yi given Xi. The argument here is exactly the same as the argument we used for the discrete memoryless channel, so the details are omitted. Then differential entropy of Yi minus differential entropy of Yi given Xi gives the mutual information between Xi and Yi. Let V be a mixing random variable distributed uniformly on the time indices 1, 2 up to n, which is independent of the random variables xi, I from 1 up to n. Now construct a random variable x by letting x equals x sub v, and let y be the output of the channel with x being the input. This is illustrated in the figure. When v is equal to 1, x is equal to x1. When v is equal to 2, x is equal to x2. When v is equal to 3, x is equal to x3, so on and so forth. Then the expectation of kappa of x, where x is equal to x sub v, is equal to the expectation of kappa of x given v. This is equal to summation I, probability v equals I, times the expectation of kappa x given v equals I. Now conditioning on v equals I, x is equal to xi. Since by construction the mixing random variable v is independent of xi, we can remove the conditioning on v equals I the probability that v is equal to I is equal to 1 over n. For this expectation, by taking it outside, we obtain expectation of 1 over n summation I kappa of xi. We assume that each code word in the codebook satisfies the input constraint. Then the input sequence x, which is a randomly chosen code word, satisfies the input constraint with probability 1. That is, 1 over n times summation I kappa of xi is less than or equal to p with probability 1. Therefore, this expectation is less than or equal to p. Now recall this picture illustrating the random variable x. By the concavity of mutual information with respect to the input distribution, 1 over n times summation I, the mutual information between xi and yi, is upper bounded by the mutual information between x and y. Previously, we have proved in step 5 that the expectation of kappa of x is less than or equal to p, and so, by the definition of C of p, Ixy is less than or equal to C of p. Thus, we have shown that 1 over n times summation I, the mutual information between xi and yi, is less than or equal to C of p. This implies that summation I, the mutual information between xi and yi, is less than or equal to n times C of p. It then follows from step 2 that log m is less than or equal to the entropy of W given W hat plus n times C of p. With the assumption that lambda max is less than epsilon, by invoking Farnell's inequality, this conditional entropy tends to 0 as epsilon tends to 0. And with the assumption that 1 over n times log m is greater than r minus epsilon, log m is lower bounded by n times r minus epsilon. Thus, we have shown that n times r minus epsilon is less than entropy of W given W hat, which tends to 0 as epsilon tends to 0, plus n times C of p. By cancelling the n on both sides and letting epsilon goes to 0, we conclude that r is less than or equal to C of p. This proves the converse of the channel coding theorem. In section 11.3.2, we proved the achievability part of the channel coding theorem. In the formula defining C of p, the input random variable x can be a mixed random variable, and so it is difficult to consider sequences that are typical with respect to the input distribution. For this reason, we need a new notion of joint typicality called mutual typicality. Recall that for any input distribution f of x, the PDF of the output random variable f of y exists as long as the conditional PDF fy given x exists. Hence, the mutual information between x and y can be written as the expectation of the log of fy given x divided by f of y. The definition of mutual typicality will be based on this form. The mutually typical set psi sub xy delta sub n with respect to a joint CDF fxy is the set of all pairs of sequences xy such that the absolute value of 1 over n times log of fy given x divided by fy minus ixy is less than or equal to delta, where fy given x is equal to the product from I equals 1 up to n, fyi given xi, and fy is equal to the product from I equals 1 up to n, f of yi. In the above, delta is an arbitrarily small positive number. A pair of sequences xy is called mutually delta-typical if the pair is in the mutually typical set psi sub xy delta sub n. Lemma 11.17 says that by drawing a pair of random sequences x and y, IID, according to the generic joint distribution Pxy, the probability that the xy pair is mutually delta-typical is very close to 1. This lemma is a consequence of the weak law of large numbers. Consider 1 over n times log of f of the y sequence given the x sequence divided by f of the y sequence equals 1 over n times log of the product from I equals 1 up to n, f of yi given xi divided by f of yi. Now the log of the product can be written as the summation of the log, and so we have 1 over n summation I from 1 up to n log of fyi given xi divided by f of yi. This is the average of the values of log of fyi given xi divided by f of yi for I from 1 up to n. And so, by the weak law of large numbers, it converges to the expectation of the log of f of y given x divided by f of y in probability, and this is precisely the mutual information between x and y. This proves the lemma. Lemma 11.18 is a generalization of lemma 7.17 that we have previously proved for the discrete case. Let the pair x prime y prime be n IID copies of a pair of generic random variables x prime y prime, where x prime and y prime are independent and have the same marginal distributions as x and y respectively. Then the probability that the pair x prime y prime is mutually delta-typical is less than or equal to 2 to the power minus n times ixy minus delta. Here is the proof for lemma 11.18. For any xy pair that are mutually delta-typical, by definition, the absolute value of 1 over n times log of fy given x divided by fy minus ixy is less than or equal to delta. Then 1 over n times log fy given x divided by fy is at least equal to ixy minus delta, which implies that fy given x divided by fy is greater than or equal to 2 to the power n times ixy minus delta. Or fy given x is greater than or equal to fy times 2 to the power n times ixy minus delta. Now consider 1 is greater than or equal to the probability that the xy pair is mutually delta-typical. This probability is equal to the integral of fy given x dfx dy over the mutually delta-typical set. As usual, it doesn't hurt to think of dfx as fx dx. Now fy given x is greater than or equal to fy times 2 to the power n times ixy minus delta. Since 2 to the power n times ixy minus delta does not depend on x and y, it can be moved outside the integral. Now observe that the measure of the integration is actually a product form, and the integration is over all sequences that are mutually delta-typical. And so, this is equal to the probability that the pair x prime y prime is mutually delta-typical. Hence, the probability that the pair x prime y prime is mutually delta-typical is less than or equal to 2 to the power minus n times ixy minus delta. We now describe the random coding scheme. For the parameter settings, we fix epsilon greater than 0 and input distribution f of x. Let's delta to be specified later. Since C of p is left continuous, for a fixed epsilon, there exists a sufficiently small gamma greater than 0 such that C of p minus gamma is greater than C of p minus epsilon over 6. Recall the definition of C of p. By replacing p by p minus gamma, we have the definition of C of p minus gamma. By the definition of C of p minus gamma, there exists an input random variable x such that the expectation of kappa of x is less than or equal to p minus gamma, and the mutual information between x and y is greater than or equal to C of p minus gamma minus epsilon over 6. That is, the mutual information between x and y can be arbitrarily close to C of p minus gamma. Then for a sufficiently large n, we can choose an even integer m satisfying 1 over log m is at least equal to ixy minus epsilon over 6, and at most equal to ixy minus epsilon over 8. Then 1 over n times log m is greater than ixy minus epsilon over 6, which in turn is greater than or equal to C of p minus gamma minus epsilon over 3, which in turn is greater than C of p minus epsilon over 2. We now describe the random coding scheme, which is very similar to the discrete case. First, construct the codebook C of an NM code randomly by generating M code words in R to the power n independently and identically according to the product distribution fx to the power n. Denote these code words by x tilde 1, x tilde 2, all the way to x tilde m. Then review the codebook C to both the encoder and the decoder. A message W is chosen uniformly from the message set. The sequence X, which is equal to the code word corresponding to the message chosen, is transmitted through the channel. The channel outputs a sequence Y according to the conditional PDF Fy given X. At the decoder, the received sequence Y is decoded to the message W if X of W, that is, the code word corresponding to message W, and the received sequence Y are mutually delta-typical, and there does not exist another code word which is mutually delta-typical with the received sequence Y. Otherwise, the received sequence Y is decoded to a constant message, and denotes by W hat the message to which Y is decoded.